So we will finalize our discussion on permeability in porous media by what is called a bundle of tubes model. And before I introduce that model, we will first look at something that is at the core of that model, which is looking at various cross sections and assuming that I have a flow through a constant cross tube of constant cross section, possibly irregular. Let's see what equation do we actually need to solve to get a solution to that flow. So let's just take a look visually with our favorites, sphere packing. So if this is a sphere packing, we already commented on most sort of fundamental unit of this sphere packing is if you take four spheres or so four neighboring spheres and look at the tetrahedron that they form, the pore space that is left in between those spheres is called a pore, and that's something that you would quantify for pore sizes of this medium. And these sides, okay, of the medium are actually the tightest spots, and those tightest spots are called throats. So if I take just three spheres that are nearby, if you kind of zoom in, you actually see a converging and then diverging cross section, right, as I go through. So this is a three-dimensional medium, but you could actually see that, like, if I take a plane through the sphere centers here, that's where my tightest spot is. So some inertial flow on the sides of this converging, diverging part notwithstanding, you could actually assume that dominant flow, or flow is dominated through the tightest, by the tightest spot, okay? And you can actually just look at a tube of a constant cross section that is going through that middle, okay? And that the flow between the two is fairly similar. So basically this is, if we do that, okay, then this is my cross section and I have oriented it vertically, so I'm actually having my tube aligned with z direction, and I'm calling the boundary of the tube omega, and then what we're actually solving, I can take Stokes' equation for creeping incompressible Newtonian fluid, okay? So my Stokes equation basically comes down to mu Laplacian of V is equal to gradient of P, and P I can just take as a generalized pressure. So then my V in this particular cross section, I will not have Vx and Vy, right? Those are zero. So I only have a Vz, okay? So Laplacian of vector V is really a vector with 0, 0, and then Laplacian of the z component, because we know that we go component-wise for z. So this really comes down to basically, and the same with pressure. Pressure really has only z component here. So basically what I will have is that Laplacian of Vz in this particular case, and that's just dependence on x and y, I don't have dependence on z, is equal to -1 over mu delta p. Delta is now difference between the end and the top, okay, divided by L. And my boundary condition is that this Vz on omega, omega being this entire boundary, is 0. This is what's called a Poisson equation, because in my general case, this delta p over mu L will be a constant, right? So I will have that Laplacian of Vz is equal to constant, right? I can also rescale if I actually replace Vz with w of xy minus this constant over 4x squared plus y squared, okay? That when I take a Laplacian of this, I will actually get precisely this constant here. So I could, this equation is equivalent to Laplacian of w is equal to 0, which is Laplace equation, and w being basically Vz plus this term here. Again, Laplacian of this term will give me this constant here. So I can just transform it to Laplace equation. Either way, both Poisson equation and Laplace equation have names because they're famous equations, and famous equations with names show up everywhere and anywhere, so there's a lot of good solvers for such equations, okay? The moment you have a name, that means that it's been solved, so you can actually go and look for either software or otherwise you can solve it. So in a general cross-section, this cross-section being irregular, this is not going to be something that is easily solved analytically, but we have a couple of solutions that we can actually rely on. They're actually listed here. So there is elliptical solution, and basically here is the VZ, as well as the ultimate flux through this type of tube. Then there is a triangle, equilateral triangle, and solution is given there. I think in one of the problems in chapter 3 BSL, you actually have this solution and you have to verify whether it satisfies Navier-Stokes or something like that. And then there is a rectangular solution. So this is actually a series solution, but approximately if you have a square, you can count on flux being 0.035, 1 times delta P h to the 4, okay, divided by mu L. Now, quiz time. For the same cross-sectional area, pressure gradient and fluid, okay, which one of these cross-sections has the largest flux? Circle, square, equilateral, triangle. Yes?
Would it be the one with the, with respect to the largest or smallest hydraulic diameter?
Well, that's, yes.
So the one that would have the highest area relative to the wall perimeter?
That could, yeah, that's a good relationship to look for. But also sort of like, so which one is that? Which one's the most effective? Circle would be most effective. Just intuitively, I don't have corners where I'm kind of losing the flow and having very small, because I know that near the corners or near the boundary, I have to have a 0 velocity, and that slows me down. Okay, so that's this area over perimeter, right? The smaller the perimeter, larger area over perimeter, so that gives you this shape factor that is favorable for flow. So yes, circle, and actually if you could also go and throw things into these formulas, at least for the square and for the triangle, you will actually get that for square duct, it's roughly 0.9 of the Q, and for triangular duct, it's a little less. So square is actually a little more effective than the triangle is. All right, so now that we know how to solve things in a cross section, this is for these are the cases where I actually do have analytical solutions, so I can actually do that. Your next computational homework will actually involve a PDETool in MATLAB that can solve the equation. And these are we are not going to go through this in class, but this is something that you will just have that you can refer to use PDETool. But basically, then you can throw in any geometry. This is one of those sphere pack cross sections, right? So this is basically how flow looks through some of the cross sections that might be irregular. And basically, you can see how in corners I'm kind of losing some of the flux because I'm not as effective. All right, so now I'm gonna finish my setup here and just quickly write the comments of the bundle of tubes model, or I might actually make my life a little easier and just show it from the last time. I think that's what I'm gonna do. So what is now, so that I save myself some writing, okay? So what is now a bundle of tubes model? I will assume I have, quite literally, across my medium, a bundle of tubes. And I can assume various cross sections for those tubes. Simplest one, of course, is the circular cross section, but that one also is not, it's the least realistic. Nevertheless, bundle of tubes model, so typically you will one way to describe your medium is to go and do mercury porosymmetry in your core, okay? And mercury porosymmetry will give you the essentially throat radii. It's pore size distribution, but it's really throat size distribution from mercury porosymmetry, because it's throats. These throats are the ones that are controlling the flow, and that's what's stopping your flow. And at the same time, you do have to take a bit of this pore throat size distribution with a grain of salt for mercury porosymmetry, because once your pressure is high enough, okay, then you will first take a moment to get to the pressure high enough to get to all of the boundary pores. And after that, you are stopped by your smallest pores. But once you overcome them, you're measuring the volume you take at the step after to actually go through the medium. And in that process, you're accessing all kinds of sizes of pores that might be also larger than the one that was holding you up in place to begin with, right? So it's a distribution, it's the best we can get often, but you do take it with a grain of salt. So in any way, you could take radii from that distribution, and you could, for some type of analysis, basically assume that you have a bunch of tubes across the medium, in any number of them you'd like, that basically have those radii, okay? And then you sum them up, right? And you will get a bundle of tubes model. So that's often done for a various transport modeling, okay? If I can actually model something in such a tube. Now, the biggest problem in terms of two-phase flow for the bundle of tubes, it's pretty good for various fluxes I'm measuring across my medium, but in terms of two-phase flow, interconnectivity of the medium is something, and rough corners of the medium is something that holds fluids and traps fluids. So there's no way with the bundle of tubes that where you have a circular tube, you cannot get any trapping of the fluid. So if you're looking into imbibition and how much of the non-wetting phase you have trapped at the end of imbibition, for bundle of tubes model, you will get, if it's circular tubes, you will get a 0. Okay. So that's something that you have to, so all models are just that, they're models, they're simplifications. Some models are more appropriate for modeling certain phenomena, some are less appropriate. Okay. So bundle of tubes is great because it's simple. Okay. I can easily basically describe my medium with a bundle of tubes, but in some cases it might be too simple. So you have to always judge what you're using. Again, none is perfect for every situation. So I could have, again, tubes, triangles, fractures. Fractured media are often just like a bundle of slits across my medium, could represent my fracture medium. And in that case, we know that the flux, volumetric flux, through one tube is some function of the pressure gradient and viscosity, right? That was my boundary condition in the Poisson equation, and some function of shape, okay? Because Vz has to be 0 at the shape. So depending on what that function is, I will have different relationships for Qt. Now, the way I relate my tubes to actual porosity, I know that the porosity is the number of these tubes times their area. So this is cross-sectional area of each shape divided by total area of my side, right? So basically, number of tubes is simply porosity times area of the side divided by cross-sectional shape area. So when I actually put that my Q, my linear flux across the tube, is basically number of these tubes times their volumetric flux divided by my area of in the entire face, as per Darcy's law. And as per Darcy's law, this is also K over mu delta P over L. Minus, but I'm disregarding minus. I'm disregarding signs here. Then when I plug things in, and T, this Qt, I will get that my permeability from these equality is overall porosity over area, of each element, or this bundle of a tube in the bundle of tubes, times this function that I have that describes my flux and UL over delta P. Actually, excuse me, this is not part of the. This is not part of the permeability. Actually, yes, it is. Yes, it is, because I have delta P over mu L inside here, and I don't know how. And if you actually plug that in for a circular tube, those are the numbers. That's the QT we know. You will actually get that permeability is phi r squared over 8. So that's basically the same as our initial discussion of carbon-Cozzeni model, assuming my tortuosity is non-existent. My tortuosity is 1. So bundle of tubes also ignores this tortuosity factor. So you can already see here how bundle of tubes will give me permeability that is, for instance, porosity r squared over 8. Okay. Whereas a tortuous tube would also be divided by some tortuosity factor, and that factor can be fitted. So yes, for different assumptions or different estimates, you're going to get different numbers, even though you're supposedly modeling the same medium. Okay, such is life in petrophysics. Because again, we're upscaling, and we don't know all of the details that will give us exact assumption. Okay, and I guess if you're not comfortable with such things, then petroleum engineering might not be the best major. Okay, so I'll quote somebody else, like if you're chemical engineering and you're designing a processing plant, basically down to the second decimal point, you know, you put stuff in and you know with a very high precision, like 0.01%, what's going to come out, right? And that's never the case in petroleum engineering. So again, because we don't necessarily design rocks ourselves, we're given to deal with the rocks as they are. Yeah. Questions?
So if that tau is not 1, that will be reflected inside the F function, right?
Not based on the bundle of tubes, it won't be, because in bundle of tubes I'm assuming straight, no tortuosity.
Okay.
So bundle of tubes simply doesn't deal with tortuosity. And that's a shortcome of the model. Okay? If you want tortuosities, you basically go to the carbon-Cozzeni model, one of the generalized models. It doesn't have to be for sphere pack, but that will have tortuosity in there, and then that's something that you can adjust. Okay? So the thing that you can adjust here is what particular cross-section are you going to go and assume, right? Okay. What cross-section is descriptive of your medium? And again, typically there's not one, so you have a range, you have some wiggle room there to adjust your formula to work with whatever experimental data you might be measuring.
But even in this model, we could have assumed that tau is not 1. And just
we could, but again, just the general bundle of tubes model has it. Now, if you actually don't assume that it's not 1, you're going to Cozzeni model. If you remember, there was a K0
right.
that basically is adjusting for the shape of the cross section.
Okay.
So you can go there.
So, would it be better to combine both of these to have two parameters to sort of vary?
But that's Cozzeni model. It will have K0 in there.
Yeah. So
Yeah.
this is a simplified bad version of Cozzeni's model.
Yes. I'm not going to use bad because in some cases it might be enough.
But Cozzeni's model, you cannot change the cross section. Like you cannot make a triangular tube.
Yeah, you can. K0. If there's that one generalization of the Cozzeni model that I mentioned, then can.
Okay.
So in our general, so Cozzeni idea was like, okay, this is going to be a circular tube, but then like this radius, I'm going to replace with hydraulic radius.
Yeah. So
And that's where you have the space to actually put a different cross section. Okay. So yes, all of these are kind of similar. And again, you're going to have a factor of 2 difference, possibly. But often in permeability estimate for more complex media, if you have a sand pack, if you have a sphere pack, those you should be able to fit parameters rather well and get a pretty good estimate. But anything more complex, you're pretty good if you're on the same order of magnitude. Okay? So the fact that all of these estimates could be, times 2 of each other, it's okay. That's what leaves you the room to adjust them because there are fitting parameters. So essentially, in original carbon Cozzeni, the one for sphere pack, you have tau, which is only tortuosity, as fitting parameter. In the more generalized Cozzeni model, you will have K0 and tau, and both of them you can adjust. Okay. And here, you basically can work with this shape and you can adjust the shape. None is perfect. Yes, this could be interpreted as a simpler version, but simple is sometimes better. Okay? If you don't have a way to constrain 2 parameters, because for that you have to have enough experimental measurements. So if you don't have that, then go simpler. Okay? So that's the philosophy of how you fit the data. All right. So this basically completes our section on permeability. And we will move on to, I will start an introduction of so-called friction factor. So friction factor will now, this is going to be chapter 6 in your textbook. It's actually going to take into account the flow regime. So far we've been working with laminar flows, mostly. We will not go into the details of turbulent flow. If you are so inclined, you can read chapter 5. We will really deal with turbulence only through friction factors. So for the most part, it's extremely hard to find an analytical solution to turbulent flow. But in many applications, you will have turbulent flow show up. In any kind of general piping, whenever those pipes are larger than 1 millimeter, you will have actually onset of turbulence and onset of turbulent flow. If you're inside of a typical porous medium formation, most often you will have creeping flow. However, if you're close to the wellbore, in a fracture near the wellbore, possibly in the propant pack that is keeping that fracture open, in all of those areas, and the wellbore, of course, itself, because it's a bit larger in cross-section, there you will have turbulent flows, so you do actually have to account for friction losses, and friction factors are one way. So let's quickly start introducing that topic. Okay. So basically we have we're not completely done with porous media applications, but we're gonna deal with some of that in this chapter 6. So basic motivation is upscaling, and not just in porous media, in just regular flow through a tube or flow around the sphere as well. So we need some estimates and measurements for some macroscopic parameters, or we call them often closure parameters. So we can measure flux, and we can measure delta P over L. I know typically what my, I can typically measure the fluid properties as well. They might be just effective properties of a complex fluid, but basically my mu summarizes fluid resistance to flow, okay, whatever that fluid might be. And my K summarizes geometric properties of the formation I'm flowing through. So I would like, so far we developed these for creeping flow. So any upscaling we've done, we actually started with analytical solutions to Stokes' equation typically, and for Reynolds numbers that were rather small. So I would like now to basically make this more general. So whatever permeability estimates we have done so far, they're all for creeping flow. So they're all for actual formation where you have rather tight pore spaces that make the flow rather slow. And now I would like to move on to different flow regimes, and we might need different relationships for those flow regimes. So we will introduce a friction factor. It's going to be a bit of an abstract construct, even though it has very practical applications. So basically it's going to be a proportionality constant that relates the drag force, which I refer to as Fk, to some sort of characteristic area of the system. So if I'm flowing around the sphere, that area is some multiple of r squared p. Okay? If I'm flowing through a tube, that area is basically area inside area of the tube, or just like even cross section. Okay? So this is where I'm just pointing out that you might have a choice of area that you're going to take into account, and that's often historically chosen for some reason or the other. Okay? And then you have a kinetic energy density that we're going to try to estimate from the flow parameters themselves. So basically I have the relationship with friction factor is the fitting factor between the drag force or kinetic drag force, this characteristic area, and energy density. And again, we want to predict the behavior of complex systems based on the measurements that have already been done. Okay? So assuming right now, especially we're in 2016, there has been a wealth of measurements done, I want to find a structured way to fit those measurements. So we know that whenever we do curve fitting, I kind of have to have an assumption of what curve do I want to fit to my data. What curve is an appropriate fit for my data. And basically, the concept of the friction factor will give us sort of like a structured way to figure out, well, what should this fit be. Okay? So essentially, it's just like one lens of it, and we will use our analytical models as guidance of what that fit should be, but ultimately we will adjust things to very realistic measurements where I don't have analytical solutions. So again, we will not neglect influence of the flow regime, but we do expect some or great dependence on actual Reynolds number, and we know Reynolds number that basically quantifies parameters or similar regimes, both in terms of the geometrical shape, so we will have to have classes of these friction factors, one for tubes, one for flowing around the sphere, one for sphere pack, so every different shape will essentially have it has its own definition of Reynolds number, and will have its definitions of friction factors. So I expect this friction factor to be a function of Reynolds number. All right. So just before we move on to that, let's just comment on Reynolds number and how it actually came to be. Okay? So it actually came to be by analyzing dimensionless form of Navier-Stokes equation. So if you start from a standard Navier-Stokes equation, we have a continuity equation. So I have an incompressible flow, so my divergence of V is 0. And then I have rho times material derivative of V is negative gradient of pressure plus mu Laplacian of V, and any gravity or force that I could have is in this generalized pressure term. So now if I want to basically make this dimensionless, I will introduce characteristic length on my system that I'm dividing with, characteristic velocity of this system, and some potential at some point so that I can actually, for instance, exit of a tube. So my dimensionless variables are then anything to do with the actual position. I'm going to divide by L0, okay? So my x prime vector will become xyz divided by L0, okay? Time, I introduced a characteristic. Time is t over t0, and basically I can get t0 by comparing characteristic velocity and characteristic length, or rather dividing them. Okay? So basically, so my t0 is L0 over V0, so you will get this relationship. And I will introduce pressure as P minus P0 over rho V0 squared. There's multiple versions of this. This will do for non-dimensionalizing pressure. Okay? So once I actually plug that in, great. I am wondering, what is the Navier-Stokes equation for x prime, t prime, v prime, and p prime? Okay. And I can simply go in this equation and replace things, I just have to be careful once I see gradient with respect to my original x, y, z, okay? I have to transform that or translate that to my x prime. So gradient with respect to x. So if I look at the partial derivative with respect to this x prime, I'm wondering what is it in terms of my original partial derivative with respect to x. And I know that my x prime is x over L0, okay? So partial with respect to x prime will be partial derivative with respect to x times partial derivative of x with respect to x prime, okay? And since x is L0 x prime, then I will get that this is L0 partial x. Okay, everybody following? So this is basic calculus. So therefore gradient is essentially my gradient prime is L0 times gradient. Okay. Similarly, you could get that this derivative is T0 ddt. So if I plug this into the original Navier-Stokes, I can obtain the dimensionless form of this. You will get that the continuity equations didn't really lose its form, and I wouldn't expect it to. And also, this equation now doesn't have mu here anymore. I actually have this number here, mu divided by L0 V0 rho. It doesn't have rho here, I'm sorry. So I divided by rho as well. What is this? It's 1 over Reynolds number. And that's essentially why we define Reynolds number the way we do. And it's, of course, dimensionless number. So basically, what that saves me is that I can solve, if I'm solving for Navier-Stokes, this is what I'm going to solve for. Okay? For two reasons. One is purely numerical. If I have dimensionless form, okay, all of my quantities will be close to 1 because I normalize them. Whenever they're close to 1 and approximately on the same order of magnitude, that will cause me less numerical issues just with representation of numbers in computers. Because if I'm adding up or multiplying numbers that are vastly different, then the result will be much less accurate when I try to store it in the computer memory. So that's just the finite memory of the computer. Second part is I can solve this once and then just basically adjust, then I've solved it for all of the similar geometries, okay? So once I get my x prime, I can then just multiply it with my characteristic length, and I can then deal with any kind of scale. So it's easy to scale this larger, and that's often used for airplanes. We don't even test both for testing them, wind tunnels. We don't test planes by building the entire plane and go crashing it, right? Sometimes they crash, they do, but that's not intentional. It's much cheaper to test the whole thing in something that is scaled, right? The wind tunnels are scaled to something that you just build your little model and you can crash it all you want. Yes?
Question. Is L not the same for all coordinates in general?
Yes, it's taken, yeah. So if I have a shape that is not, otherwise I would have, you could still probably go and do, but then it's a little more complex too. It's not a Reynolds number anymore. It's hard to define a Reynolds number. So it's still taken as the same number. Okay. So this is basically, for two reasons, we actually want to solve this non-dimensional Navier-Stokes equation. Okay, so that's the Reynolds number. And again, part of this discussion is that I want to look at the friction factors as a function of Reynolds number. And I will not start any detailed approach today. I will just kind of overview where it is that we're going to get at the end of this chapter. So we will study flow in cylinder, which is a proxy for flows in channels and tubes. Flow around sphere, which is a proxy for any flow around objects. or any submerged objects, and flow through sphere packs. Obviously, we want porous media, so we would like to look at something that is similar to a porous medium that we often use. And each of these sections will start from laminar flow. So in laminar flow, we know our analytic solutions, we will look at them for motivation. Then I will, based on those analytic solutions, I will figure out how to define a friction factor using some measurable quantities. So I can always measure my gradient of pressure, for instance. I can actually measure these areas that I'm interested in, things like those. And then I will check the definition with this theoretical definition with experiments, and it turns out that F can essentially be defined as a function of Reynolds number, so we will actually possibly for different regimes, I'm going to have a different function, but my friction factor will be a function of Reynolds number. So it's going to look like something like this. So this is for flow in a tube. There is no data here, but all of these lines are actually, there's underlining data that I fitted this line to. So basically for friction factor for a tube, we will be actually able to compute it's 16 over Reynolds for laminar flow regime that typically goes up to 2100 Reynolds number. And then after that, I will have different definition, assuming a super smooth tube, which we never have, but oh well. Then my friction factor becomes 0.0791 divided by Reynolds to the 1/4. Okay? But if I have a difference, this is the scale of my roughness of the tube. So if my tube has roughness that's when divided by tube diameter is around 0.004, then basically this is the line that describes my turbulent flow. And of course, for turbulent solutions, that roughness of the tube will give you different flow flux as a result. So basically, for different roughness, we will have different functions. So this is going to be sort of our summary for flow in a tube on any scale. So you basically go to this based on the size of the tube that you're looking for any friction losses. Then for flow around the sphere, we will actually, so this is just to give you an idea, we know that already that our drag force Fk is 6p mu RV infinity, right? So that's analytical solution for laminar flow regime. And my characteristic area will be r squared p, so that's basically a projection that I see when I'm flowing towards the sphere. And again, this is where I could have chosen 4 r squared p, but that factor of 4 is really irrelevant. And then my kinetic energy density, I'm going to quantify it in terms of this approach velocity towards the sphere, V infinity squared. So it's going to be 1/2, this is kinetic energy density, 1/2 rho V infinity squared, and that basically gives you the friction factor for tube. So what is it? Can you do a quick calculation? What is F? Friction factor F. In terms of everything else. I want it actually in terms of Reynolds number. So try to find the Reynolds number in there. What did you get? What is the definition of Reynolds number for a sphere? Yeah, so 2r, you have to use diameter, right? This is what you should get. Okay. So it's going to be 12 mu divided by r rho v infinity, okay? Which is 24 over 2r rho v infinity. And for Reynolds number for sphere, we have to use the diameter. Yes?
The area.
Again, this is the agreement. So in a friction factor, I'm taking some specific cross-sectional characteristic area. And for sphere, I'm simply defining it as R squared.
No, I think the equation.
Oh, this is just the definition of friction factor. So I'm starting from that initial definition. So K is this friction loss, essentially, is the drag force. Okay, and then A is characteristic area, K is kinetic energy. Again, how do you define characteristic area and characteristic kinetic energy for the system is a matter of agreement. Okay, I would arguably use 4r squared p, but that's just me. But somebody started it as such. Again, up, down, as long as you know what the agreement is, it doesn't really matter, it's just a factor. Okay, so my F is 24 over Reynolds. Okay, and then these are the different flow regimes. Now, this is basically the friction factor for the flow regime we actually solved here, so it's 24 over Reynolds. However, with Reynolds, and we said that it's basically, this is valid for Reynolds less than, test was last night, less than 0.1. Wow, that's a good question for a future test, it seems. Okay, so it's less than 0.1. And then for anything larger, basically, you will start having eddies, and there's this turbulent wake behind the sphere. And the separation point indicates that basically you have bifurcation of the solutions. So turbulent solutions are not unique in themselves, so there will be multiple solutions admissible by Navier-Stokes equation. It's a nonlinear equation.
Well, why did the eddies go away in the last image? Why did the circular things go away?
This is just observed flow. So at some point they're just like too big, so they don't circulate anymore because the stream is too strong. So you're not gonna, it's almost as if this stream is not even seeing the sphere, right? It doesn't bother it. Okay. So again, we will go through, we will comment on this a little more, but basically, so this is the part where we have very small Reynolds number, and yes, actually up to 1, it's actually just fine to assume that, that same formula, 24 divided by Reynolds. And then after that, you have a different relationship with the Reynolds number. This line here, again, is fit to experiments. Okay? So it's fit to experiments, and basically then after that some point, you can just really use a constant number if you wish. Okay? So we will go in a little bit more details for this. And finally, for sphere packs, same thing. Here we actually have the experimental measurements.